And now let's look at another example to the equilibrium. They said for this frame, there's a 4 kilonewton load at B and the support at pin A and C. Find the reaction support at A and C. So intuitively, if we're drawing FBD, we know A is going to be a pin support, so we have AX and AY. Also, the C is a pinned support as well, because AB and CD is connected at this pin C, so we'll have CX and CY. Of course, we have this 4 kilonewton at B. Knowing that, let's look at this FBD number 1. We have 4 unknowns, right? AX and AY and CX and CY. However, we want to have 3 equations. So we can already solve this problem. That's the uniqueness of this problem. When you have that, you just realize, oh, we're stuck. But actually, we're not stuck. The reason behind it is we didn't see one special feature, which is two force member. One of the video earlier is just about two force member. A quick review: two force member is a member that has forces acting on two different locations, right? And because of this, we know CD is a two force member. One force at D, one force at C. And ACB, however, is not two force member because they're force at A, force at B, and they're also force at C. CD is going to be two force member. And the characteristic of two force member is they have to be, well, for example, this is my two force member. I have A and B here, forces at A and force at B. They have to be what? Equal and opposite and collinear, which means if I connect those two, they're going to be on the same line. Now let's think about the CD member. If I were just looking at CD member itself, I'm drawing FBD number 2. Just look at CD out. I isolated out. If I assume its intention is member, they have to be connecting C and D and those two forces, right? So in knowing that, it's going to help us draw this FBD number 3. So F number 3 is I'm going to redraw this beam A, C, B. Remember at FBD number 1, we draw on our first attempt. We have 4 unknown. Now let's see if we can just have 3. We have AX, AY, because it's a pinned support. However, at C here, it's different now because we know CD is a two force member. And also, Newton's law. So if we're going to call this, it's going to be C, the force at C. Newton's third law, every reaction have equal but the opposite reaction. So if this CD is in tension, so where's this force coming from? This force is coming from the beam AB. So basically beam AB, or like this point C, is pulling CD this way. Then Newton's third law, CD is going to be pulling back, right? So CD is going to pulling back in the same direction as CD, right? In the same direction as CD. So here, the reaction here, I'm going to call this, how about we call FCD? Because we know it's along the line of C and D. And if we want to know the direction, the geometry, so this is 1.5, this is 1.5. It's basically 1, 1, right? So we can go ahead. See, this is going to be 1, 1. That's the slope here. Then at B, we have 4 kilonewton. That's gonna be our FBD, because now we just need to solve FCD. AX and AY, those are only 3 unknowns now. So let's go ahead and solve out this problem, okay? So we'll have some forces at X direction. We have AX. And FCD also have X direction. We're solving FCD. However, X direction is 1. Hypotenuse is 1 square plus 1 square take square root 2. And its x direction is pulling to the what? Pulling to the left. So it's minus. That equals 0. Now forces at y, we'll have AY going upward. And FCD have y direction. Vertical is also 1, so 1 over square root of 2. Hypotenuse is going downward, so it's minus. Then we have this 4 kilonewton going downward, equal to 0. Then the very last one, we're going to do moment. Let's see, what do we do moment about? Have a lot of forces going on, so if we do that, we'll choose point A. If we choose point A, AX, AY will not show up because the force going through point A, so the moment will be 0. Now let's look at FCD. FCD, our X component, is right here, right? Y component is here. X component also going through point A, so that's equal to 0. Then we just needed to look at Y component. Y component is, that's the force, right? 1 over square root 2 times FCD. And that's the force, but how about moment of arm? Moment of arm is going to be from A perpendicular to that force. It's going to be here. And how far is that? It's going to be our 1.5. Now let's think about the direction or rotation. This force rotating about A, it's clockwise, so that's negative. Okay. So far we have worried about AX and AY rotating about A equal to 0. We're also thinking about FCD X direction, rotate A is equal to 0, and we did FCD Y rotating about A right here. So that's going to be FCD Y direction rotating about A. Now the last thing we need to worry about is 4 kilonewton and rotating about A, so which will be the entire beam length for moment of arm. That is 1.5 plus 1.5. That rotation is going to be clockwise, so that be going to negative equal to 0. Then let's see. Pause for seconds what you got for those answers. Alright, so I had this answers as shown here for our FCD and AX and AY. So once we have that, we're going to be able to, we actually solve this problem. So they're asking the support reaction at A and B. At A, since we find AX and AY, we can, this is something I didn't do in the previous video, but we can. So reaction at A, if they wanted to find one reaction, the basically resultant, you are just going to using AX squared plus AY squared, right? Since you find it's basically 2D resultant for square plus A squared. And then let's see, what do we have? And I think we know, right? It's going to be 10. Because that's give us to be 100. Okay, so that's going to be 10. The unit is going to be kilonewton. Okay. So that's going to be the reaction at A if they want you to find one force. And then again, you can even find the direction. What direction it goes, so you can use inverse tangent of AY over AX. So that's basically the 2D resultant. Also, in order to find a reaction at C, that's basically your FCD. That's 8, negative 2 kilonewton. Negative. For this situation, if it's negative, corresponding to our reaction FBD number 3, which means the true direction is pulling that direction, right? But we don't need to go change it because that's corresponding to the right one. Okay, so that's all we have for this problem. And hopefully you can see the 2D member play an important role when you're solving equilibrium problem. When you identify them the earliest as possible, that will help solving it. All right, see you next time. Bye.